I'm going to start my session. So in my last class, I have already started with the discussions of electronic instruments, especially digital instrumentation. So that was the introductory class. So I told about different characteristics, okay, different characteristics, motivations and classifications of digital electronics, okay, based instrumentation. So some important features some important features was discussed, and it means why digital electronics are why digital instruments are most beneficial. Sometimes it is most advantageous over your analog instruments. Okay, so some of the important features I told about you, like advantages. Okay, some of the disadvantages that I have already discussed, and I think all of you gone through these points and you have prepared your class note. Okay, so I hope you will understand that what are the most important features, okay, of digital instrumentations. Okay, so what are the most important features and that benefits of their features and their benefits. Okay, so here you can understand that important benefits was like your low signal level signal, so there is some amplification detection of low signals, high input impedance, low power consumption, high frequency range, different advantages was there. Okay, so that I already discussed. Then some of the disadvantages, then I discussed about the performance characteristics of digital meter. So why we are selecting the digital meter over the analog meter based on their application resolution, accuracy, error, monotonicity, settling time, and finally the temperature sensitivity. That point I have already discussed. So today I am going to discuss about some specific applications of digital instruments, like digital multimeter. Okay, so like digital multimeter, then frequency meter, I think so, digital voltmeter, DVMS, then digital frequency meter, and finally signal generators. Okay, so few important points are there, so that I am going to be discussed in my today's session. So you can see that digital multimeter means, I know that all of you are aware about that analog multimeter. So same thing, only that display is different in case of digital multimeter. So what is digital multimeter? Okay, a digital multimeter is an electronic instrument which can measure very precisely the DC as well as AC voltage, current, okay, and the resistances. Okay, so it is able to measure DC and AC both. DC and AC both you can measure. So there is a options for measuring voltmeter, ammeter, measuring options of voltage, current, resistance. Normally this all are we can check. We are also doing some other tested by using digital multimeter, like continuity test. Okay, so by this continuity test we can understand is there any short circuit path is there or not. Okay, so different applications are there, and we can define different applications and features are there. Okay, and we can go for that measurement by using digital multimeter or any digital meters. Okay, all quantities other than DC voltage is first converted into the equivalent DC voltage by some device, then measured with the help of digital voltmeter or different issue. So that different thing. So the main thing is that you are able to measure voltage, current, resistance, okay, and other different testing also sometimes possible, like in you can also sometimes measure, you are able to measure sometimes capacitor, inductor values, okay, the resistance of that, means that configuration of your transistor, diode, different features you can add over there. So here you need to know about the very basic block diagram of your digital multimeter. So you can see over there DC voltage is there and input you are given. Okay, different channels are there. Then ohms means it is able to measure that resistance. Then AC voltage is there. You can measure to able to measure the AC voltage. Then AC current, DC current. Okay, so then calibrated attenuator. Okay, so normally what happened that one standard value should be required. Okay, so that standard value is there for the calculation of error. Okay, so then you have some data. Okay, so you have some data and you are able to measure it. Okay, so what are the specifications and what are the points here you can observe it. So calibrated attenuator. So calibration is most important thing. Basically, why that calibration is important? So if the calibrated values are not there, so you are not able to mitigate that error. Okay, that's why it is called attenuator. So buffer amplifications also be required. Okay, so buffer amplifications means that value, if that value is very less, so sometimes you need to go for that amplifications. Okay, otherwise what happen, that analog to digital conversion. So all the cases, okay, so you are measuring that analog input and your output is digital output, means you have some display over with you. Okay, so you want to see that values in the display of your instrument. So that's why analog to digital converter is important. Okay, so means you are measuring quantity is analog. Okay, but your output is digital output. Okay, that you can able to see. So that's why all those things are there. So shunt path, AC, DC current, all the cases shunt path will be there. You know that configurations. Okay. So details configuration is look like your normal configuration of voltmeter, ammeter, everything. Okay. So but the arrangement and orientation is different. Okay. That's the basic benefits of your digital meter. Okay, so here you can able to find out that precisions of AC DC converter. Okay, then sometimes you also require some current source, and finally you are able to see the display. So one of the specifications you are going to be measured, so it is a block diagram of current to voltage converter. So current you are given. Okay, so now you have to find out which resistance path is you are choosing over there. So that is important. So that amount of current you have to know about it. If that high low resistance means that all the current is able to pass through this path. Okay, if that value is low means it can able to carry high current. Okay, if that value is very high means it path is able to carry the low current. Okay, but it depends upon the range of that current of your IR circuit. Okay, that means IR path current, you should define that how much current is flowing over that path. Okay, that path is very low, so definitely that low resistance you need to be picked. Okay, so then you can see the ADC to the DAM. Okay, digital multimeter. So all the cases that analog to digital conversion, due to the conversion of analog to digital, so ADC converter is always be with your instrument. So that's the important things. So what are the most important points? Okay, that I am going to discuss. For measurement of AC voltage, okay, the input voltage is fed to the calibrated compensated attenuator to the precision of full wave rectified circuit followed by the ripple reduction filter. So it is mentioned that first that all the cases, okay, all the cases that DC voltage or AC voltage, those voltage you are given over here, first it is converted to AC. If it is AC is there, definitely it will convert it to the DC. Okay, then you can go for that other purpose. Okay, so first you have to convert it from AC to DC. Okay, so input voltage of it to the calibrated, compensated, attenuated to be the precision means accurate full wave rectifier circuit followed by the ripple reduction filter. So all are there. So calibrated value, how much value is your input, and after converting, how much value you are obtained. Okay, so what is their actual value? Okay, and what you are obtained. Okay, so both difference you have to be calculated, and you have to find out that value of then you are mitigating that amount of error, and finally you will get the ripple free output. Okay, that signal you have to be analyzed. Okay, so how do ripple free that output voltage signal? So simple thing, you are using filter circuit, that is enough, to maintain that ripple free configuration. Okay, the resulting DC here, the resulting DC is fed to an analog to digital converter ADC and the subsequent display system. So all the calculations is done in your analog platform. So you have to convert that analog signal to the digital signal. How do you convert it? By using ADC, that means analog to digital converter. Many of the manufacturers provide the same attenuator for both AC and DC measurement. Okay, so that attenuator you are using, so most of them, so cost efficient manufacture, those are very cost efficient. Those manufacturers design that converter in cost efficient converter, so they are using an attenuator that is capable enough for measuring AC and DC, both of the measurement. Okay, I think all of you are able to understand. The next point is the current measurement. Okay, so first one is your voltage measurement. Now we are going for the current measurement. Okay, so in current measurement, the drop across the internal calibrated shunt. Okay, that also internal calibrated shunt. Why it is called calibrated? Because that any instant that value should not be changed. Okay, all the necessary conditions, that value should be the standard value. If you are designing on shunt resistance or series resistance, if you are designing for 10 ohms, so all the conditions, that value should not be changed, it should be the 10. Okay, is measured directly by the ADC in the DC current mode. Okay, and after AC to DC conversion in the AC current mode. Okay, so then we are converting that one by using ADC. The drop is often in the range of 200 MV corresponding the full scale. So they are taking an example. So how much drop may be there? Okay, so considering average dropping, it is observed that 200 millivolt. Okay, that is very less. Okay, not a big one. Okay, so next point is due to the lack of precisions in the AC to DC conversion, the accuracy in the AC range is generally of the order of 0.2 to 0.5%. Okay. In addition, the measurement range is often limited to about the 50 Hz. So we are using that power frequency level. So in our normal application, so in our normal indoor outdoor application in Indian culture, so that IEC electrical Indian electricity code. Okay, as per is our configuration, we are using 50 Hz. Any of the cases. Okay, so normal power frequency is 50 Hz. Okay, so power, it is lower power frequency, and due to the ripples of the rectifier, signal become the non-negligible percentage of the display. Hence, the result is fluctuating of the display number. So, whatever there is some chances of in my last class I told you that in case of digital instrument, as their sophistication is more than your analog instrument, so sometimes it may be fluctuating in nature. So it is fluctuating on its place. Okay, so if you are using that accurate value, so you can able to reduce that value. Okay, that will reduce the fluctuations. Okay, that also be possible. So as per your calibrated value, and how do you analyze your frequency? Okay, that is important. So if you are able to analyze all the switching frequencies, so you can able to do it. There is no problem on it. Okay, so and it is very simple. Okay. So the higher frequency and the detections of the performance of the ADC converter limits to the accuracy. So ADC converter is analog to digital converter. Okay, so what happened? ADC is a switch like that way. Okay, switch. So that frequency define the switching frequency define the output voltage or output signal. Okay, you have that continuous signal with you. Okay, so that continuous signal is passing through a switch. Okay, so you are giving some of the pulses to the switch. Then what happen when that pulse is, when that switch is triggered, means positive pulse is coming to the switch, then switch will be shorted. When switch is closed, then continuous signal is flow to your switch. Then again that switching signal is removed, then that means that PWM means pulse width modulation, so that off time is coming, so then switch will be off, so your output will be discontinued. So analog signal will give you the zero output, basically switch is on, switch is off. So simultaneously that process is going on, switch is on, switch is off, switch is on, switch is off, switch is on, switch is off. Due to that process, then your constant signal will give you the discrete value. Okay, that means when switch is on, you will get that value. When switch is off, you will not get any value. So discretized value all the time you are getting from the ADC. Okay, so how accurately you are getting that value? That depends upon the cost of the ADC. If it is very costly ADC, so most of the data it can be fetched. Okay, in the conversion of analog to digital value. Okay, so that depends the limit. There is some limitations of accuracy. Okay, so in AC measurement, the reading is often the range of is often the RMS or the average value unknown current. Okay, so that means you know that one, that any measuring devices you are measuring that value, instantaneous value. Okay, so that will provide you RMS value. Okay, in DC it is for providing you average value, in AC you are getting the RMS value. Okay, sometimes for measurement of current, the current to the voltage converter may also be used as the block diagram is given in the figure. So that figure is given. Okay, so it is the generalized figure. So at the time of exam, what happens, some of the theory will come from the short note type of theory about the different digital meter. Okay, so that question may become how to work that digital voltmeter, maybe digital multimeter for the measurement of current, for the measurement of voltage, for the measurement of unknown resistances is discussed with the proper mathematical justifications with diagrams. Okay, so you have to solve it and you have to write all those things. It's like the short note type question. Okay, sometimes what happens, small numerical problem may be included with that question, so you have to solve it. Okay, but the most of the concept is like your previous one concept, previous theory I have already discussed in this for this class. So most of the theory is like that way. Okay, so now here you can think about it, the comparisons. Okay, the comparison between the analog and digital meters. So what are the advantages of analog meter and what are the disadvantages of digital meter? And advantages and disadvantages of analog meter, advantages and disadvantages of digital meter. So that we need to study. Okay, so in analog meter, what happens? No external power supply is required. You know that one. But in digital meter, definitely external power supply is required. Otherwise, how that switches solid state device will work? Okay, so definitely, so additional sources are required. Actually, in analog meter, so you are using that direct physical, that means that electrical components like electrical parameters like voltage, current. Directly, you are that current is flowing through this converter circuit like that way. Okay, but in digital meter, so adding, if you provide that power or that means current or voltage to the device, after that it is able to measure that one. Okay, so additional external power source is required for your digital multimeter. Okay, so visual indications in change is reading is better observable. Okay, so visual indications means you can able to see that results. Okay, less observable means in case of digital multimeter you are not observe that variation. So directly that data is, the result is given in the display board. So it is not observable in digital meter. But analog meter, you are able to see that how it is working. Okay, it is fluctuating. The pointer is fluctuating. You can see that results. Okay, less effect of electronics noise, more effect of electronic noise in digital sheets. Definitely in analog meter, that electronic noise is less, you know that one. Basically there is no effect of interference, no effect of electromagnetic interference, no electromagnetic EMI and EMC. Okay, so you can understand. So less interference is there in case of analog instrument. So digital instrument, definitely interference will be high. Okay, it is less accuracy. So accuracy level is less. Here the accuracy level of instrument is more. Okay, so from the concept you can know that accuracy level should be more. Less isolation problem, more isolation problem. So in this case analog instrument, you are isolations, if you provide that isolation, so you have to use some isolation transformer. Okay, then for difference of their ground. Okay, so why that ground should be difference for for your power line configuration, power line network with your measuring network. If ground is not, if ground is same, then what happen? Any kinds of fault is occurred in your power line. So that fault directly reflected, okay, to your control circuit or to your measuring circuit. So that may cause the damage of your measuring instruments. Okay, because that power line may be in transmission section or not, like all the cases. Okay, if you consider like that way. So in CTPT measurements, I discussed about this point. Okay, so very high voltage line is there. Okay, so extra high voltage line means EHV line is there. So any kinds of fault in EHV line, and that is reflected to your control circuit or the measuring part. Okay, measuring circuit part, then there is a chances of that burnout of your measuring devices. Okay, so that's why ground should be isolated. So that option in analog multimeter is less compared to your digital multimeter. So in digital multimeter, easily you can do it by using opto isolators. Okay, optical isolation you may use over there. Then interference of the output with the external equipment is not possible. Okay, so interference not possible here. Definitely that interference of external instrument with that output reading is possible. Okay, simple in construction, the very complicated construction. Basically all those things will be accommodated in the single or the compact form, single and compact form. That's why the complicated constructions is observed. Big in size and it is small in size. Low cost, definitely it's a cost efficient instrument. It is more costlier instrument. The output is ambiguous in many times, that unambiguous reading due to digital indications. So those are the technical person, they can only see that how much voltage reading, how much current reading, power reading, okay, are there, because the in a multimeter. So all the time pointer is moving from its initial position to means actual position. So you have that person only can, the technical person only can read out that value. But in digital meter, directly that value is showing to the digital display with unit. Okay, in display plate, after the unit also been mentioned. Okay, so anybody can see and tell you that value. Okay, so that's why the digital multimeter is more beneficial compared to your analog multimeter. Okay, so definitely one few of the problems are there. Basically, that costing value. Okay, that is different. So I think all of you are able to understand the comparison between that analog and digital multimeter. Okay. Now the next one is your digital voltmeter. So it is called the DVMs. Okay. So in DVMs, what happened? Digital voltmeter. So normally in analog voltmeter, what is the problem? There is no problem. But you are you want to go for very sophisticated sophisticated applications. Okay, so that's why you are changing your system from analog to digital. Okay, so that's the basic motivation. So what is digital voltmeter? It display the measurements. Okay, what type of measurement? AC and DC measurement of voltage. Okay, so it is showing you the measurement of AC and DC voltage as discrete number instead of a pointer deflections on a continuous scale as the analog instruments. Okay, so pointer deflection will be there in continuous scale, means analog scale, but here the pointer deflection is not there. It is versatile. Okay, it is written like that, versatile and accurate instrument that is employed many laboratory measurement applications. Because of the development and uh, perfections of IC modules, the size, power consumptions, and the cost of the digital voltmeter has been drastically reduced. Okay, and therefore the DVMs are widely used for all the measurement purpose. Okay, so that's the reason for using the DVR. So then we can see the block diagrams. Okay, so it is the block diagram of digital voltmeter circuit. Okay, so we can observe that pulse generator. Okay, so some of the input you should give. Okay, so all the cases digital instruments, so there is some energy storing, not like energy storing, data storing elements. Okay, so some of the portion is always be there. Okay, so it is the block diagram of simple digital voltmeter given in the figure. The unknown signal fed to the pulse generator which generates the pulse whose width is directly proportional to the input unknown voltage. So here you can see in digital, any of the digital meters, so some they can store their data most of the cases. Okay, so if they are able to store their data, so you can analyze those data. Okay, as per your convention when it is required. Okay, here you can see some unknown. Okay, so some input voltage is shown, is given to the pulse generator. Okay, so some input voltage, unknown voltage is given. After getting that unknown voltage, so pulse generator will generate some of the pulse. Okay, some pulse is generated. Okay, then that pulse, here you can see it's an AND gate. Okay, AND gate is there. Okay, that is multiplied with some of the other, you can say like the monoshot. Okay, so very high frequency signals. Okay, very high frequency signal, but it having regular intervals and it's look like a impulse signal. Okay, so AND gate means what? AND gate means it is ANDing, means multiplying. Okay, so here you can observe that pulse width is more. Okay, thick, so it is multiplying with your, it is multiplying with your high frequency signals. Okay, then what happened after multiplying? So that amount is high, means it will give you that high signal, and rest of the portion will give you the zero signal, because any of the value multiplied with zero, definitely it will zero. So impulse one only giving you that response, so only you are getting the response only for that impulse signals. Okay, and finally that NAND gate is there, no, NOT gate is there. Okay, so NOT gate, it's reverting that value and the counter is there. Okay, so after counter what happened? So counter means it is counting, so you can see, you can call like the reconstruction of the signal. So first you are giving unknown value. Okay, unknown value of resistance of voltage. Okay, then it is multiplied, sorry, in pulse generator what happened, that value is compared, unknown value is compared with some repeating signal. Okay, means you can say like the triangular signal, like that way. Okay, so multiplying with that signal, and finally you will get some of the pulse. Okay, big pulses are there. Okay, and that pulse is multiplying, because AND gate is there, that pulse is multiplying with very high frequency discretized signals. Okay, high frequency discretized signals. After multiplying you will get some of the signals, that width is the width of the pulses. Okay, but the rest of the portion is goes to be zero. Okay, that is totally zero. Beyond that pulse, before the pulse it is zero, after the pulse it is zero. So only that thickness is look like the thickness of this pulse. Okay, and you are getting only the discretized value. Then what happens, not get is that it is inverting. Then counter, what is the purpose of this counter? So it is reconstructing. Okay, so it is counting all those values and reconstructing that equivalent digital value, and show you the display, and that decimal value is given to the display. Okay, then after sometimes that pulse generator will give you the reset pulse, that of digital signal. So all the times input signal is given, so definitely one signal is go to your display signal to reset your previous value, and the rest of the portion is taken care about the give you the actual value. Okay, so here you can see the representation of deviation using the block. So input voltage you are giving, then attenuators are there, so ADC, analog to digital conversion, then counter is there, and finally read out the device value. Okay, so you can see the block diagrams, okay, that DVM block diagrams. So what are the most important points? You can say like that train of pulse, that monoshot I am telling you, the train of pulse, that high frequency discrete pulse. It is called the train of pulse, this one. Okay, so this one is known as the train of pulse. Okay, it is called train of pulse. So what is written over here? So we need to understand the output of the pulse generator. The output of the pulse generator is applied to one leg of the AND gate. So here the output of the pulse generator is applied one leg of the AND gate. Okay, the input signal to that to the other leg. Okay, the input signal means this one. Okay, that is pulse train. AND gate is the pulse train. So output of the AND gate is the positive trigger train durations t second, and the inverter converts into the negative trigger train. Okay, so not gate is there means inverter, so it is convert that impulse train to the negative impulse train. Okay, then what is the function of counter? The counter counts the number of trigger in t second, which is proportional to the voltage under the measurement. So the counter is counting the number of trigger value, that one trigger value, that is the value of your voltage. Okay, thus the counter can be calibrated into the indicated voltage in volt directly. Okay, so you can go for that calibration directly. Thus the DVM described above and the analog to digital converters. Okay, so analog to digital converters is there, which convert the analog signal into the train of pulse. Okay, the number of which proportional to the input voltage. So number of pulse train is proportional to the input voltage, that one pulse train. Okay, so a digital voltmeter can be made by using any of the analog to digital conversions method. Okay, analog to digital conversion method, and can be represented by a block diagram shown in figure that I have discussed. Okay, so the DVM can be classified into the basic of ADC use. So how much range is there in DVM, means digital multi-voltmeter? Okay, so its range may vary plus minus 1 volt to plus minus 1000 volt. Okay, its limiting the accuracy is as high as 0.005% of the reading. So accuracy is 0.5. So limiting the accuracy means error is very less. Okay, 0.5%. Error is approximately 0.5%. Okay, its resolution may be 1 part of 10 to the power 6 given 1 microvolt reading, the 1 volt range. Okay, so if you give 1 volt, so how much error will be there? 1 microvolt. Okay, so that error is too less, and that device is more accurate. It has the high input resistance in order to 10 mega ohm, so very high input resistance. So that's why analysis will be very good way. Okay, the input capacitance in the order of 40 picofarad. So you can understand the ranging of that application, as well as that how much values are there. So all the thing you are able to understand for digital voltmeter. Okay, so now we can go for the next devices. You can say like the digital frequency meter. Okay, so in digital frequency meter we are going to be measure for what? The digital instrument that can be measure and display the frequency. Okay, measure and display the frequency of any periodic waveform. So if you put input signal to the unknown frequency like that way, so attenuator is there. Okay, so if you put over there, so Smith trigger, you know the operation of Smith trigger. I think analog electronics class it is covered, that Smith trigger operations, everything. Okay, it's very common thing. Okay, so it operate on the principle of the getting unknown input signal to the corner to the predetermined time. Okay, counter for the predetermined time. So sometimes you are getting that how much values of time period is there, you have to be calculate. For example, the unknown input signal were gated into the counter exactly 1 second. So gated signal is there, it is given 1 second. In the time range you are able to measure that value. Okay, how much millisecond means 20, that you can go for the calculation. The number of the count allow into the counter would be precisely the frequency of the input signal. The gated the term gated comes from the facts of the AND and OR gate employing for allowing the unknown input signal into the counter of that accumulated. Okay, so here you can see that input signal is there. Okay, after getting the input signal, so attenuator is there. So then that values is passes through your attenuator, then Smith trigger, then you will get some of the signal over there. That signal look like the pulse. Okay, then gate enable signal is there, so it is coming from the clock. Okay, from the clock it is coming, then driver is there, then you are comparing that clock signal, so gate enable signal with your pulse one. So finally you will get some of the clock signal. After the gate, and gate is there, so that counter is counting that value, so how much values are there, so that is proportional to the frequency. And decoder and display unit, so analog to digital, so clear reset pulse, so that pulse some same for the frequency as input. So input side frequency, that input side frequency is similar to your generated pulse. Okay, from the clock, sorry, generated pulse from the Smith trigger, both should be same, and that frequency and the clear or reset frequency should be same. Otherwise what happens, so if both are the signal is not synchronized, so it will be resetting that different value. Okay, that is not acceptable. So here you can see that unknown input signal. Okay, so initially it is sinusoidal in nature, so you are converting the signal to the astable multiplier. So Smith trigger is an example of a astable multiplier. So you are getting one pulse PWM type. Okay, square wave type signal. Okay, and your gate signal is there. Okay, so your gate signal is there, so when and one clear is also be there. Okay, so what will be your output? So that means when it will on, gate is enabled, so that output will be on. Okay, so how much value, how much time it will be on, because when your unknown input signal again it will be on, so it will be on up to how much. When it will be on means it is AND gate like that way, so it is on from the clear value. Okay, so it is given on, so it is turned on, means sorry, clear value is turned up, so it is on. Then here this condition it is on, then it will be on up to that both of the values on, so here it is on. Then after that what happened, after that it will be off automatically, so automatically that how much value is in gate, it doesn't matter, it will be off. Then when it will be on, then at that point again it will be off on, so again the up to this portion it will be on, then off, like that way it will going to. Okay, so T1 to T2 it is shifting, and you will get that pulse like that way. That time T is defined the in between the pulse lines between T1 and T2. So what are the most important application means operations process? One of the most straightforward method for constructing the frequency counter is shown in the figure. Okay, so that simplified form is the consist of the counter with associated with the display or the decoder circuit. Okay, the clock oscillator, driver, and then AND gate. Okay, so what are that circuit component that I told you? Okay, so all the circuit component, and the counter is usually made of the cascaded binary code decimal. So BCD, you can say like that, cascaded binary code decimal. The counters and the display or the decoder units convert that BCD output into the display for the easy monitoring. So you are able to monitor easily, okay, because you have that this BCD monitor, BCD counter. That means you are converting all those value to the BCD, okay. So the gate enables signal of known as the time period is generated with a clock oscillator. Okay, so here you can see the clock oscillator is there. Okay, so clock oscillator, that one, clock oscillator. So and the driver circuit can apply to the one leg of that AND gate. Okay, the unknown signal is applied to the other gate, that is AND gate, and act as a clock for that counter. Okay, the counter advances one count for each transitions of the unknown signals. Okay, and at the end of this at the end of the known time interval, the contents of the counter will be equal to the number of period of the unknown input signal have occurred in the time interval t. In the other word, the counter content will be the proportional the frequency of the unknown input signal. Okay, I think all of you will able to understand that I discussed over here, that is written in the form of language. Okay, exactly 1 second, and the unknown input signal is 600 square wave. At the 1 second counter will be counter up to 600, which is exactly the frequency of the unknown input signal. Okay, so it is depend upon your operation that I have been discussed. So clock oscillator, driver, Smith trigger, attenuator, all the main factors, all the main components uh, of your digital frequency meter. Okay, so it is your block diagram, then how it will work. Okay, that is defined. So here you can see one AND gate is there. AND gate is compared with your pulse that is generated due to the input signal or the of unknown frequency, and compare with your gate enable signal. Finally we'll get some of the output. That output is counted, that means fetched by the counter, and it will calculating how much values are there. Okay, after getting that value, it will give you that on output and provide you the time period of the unknown signal or the unknown frequency. That's the basic motivations for digital frequency meter. Okay, after that we can go for that signal generator. What is the purpose of the signal generator? Okay, so you know that in analog electronics one important term is called that function generator. Okay, so function generator purpose was there for generating different functions, like that you can say like that triangular functions. Okay, triangular signal, sinusoidal signal. Okay, rectangular signal. Normally we are getting different signal from the function generators. Okay, different pattern of signal. So in signal generator what happened is numerously known as the test signal generator. So normally in digital platform, not like only digital platform, analog platform, we are also using different signal generator that is used for the testing purpose. So as per the requirement you are developing the signals. Okay, the tone generators, like the test signal generator, tone generator, arbitrarily waveform generators. Okay, so what are the applications you can see over here? Okay, so frequency generator, digital pattern generator, function generator. So different options we are using here. Okay, so it is an electronic device. Okay, it is an electronic device which produces the repeating or the non-repeating electronic signal, either analog, either digital pattern. Okay, so as per your requirement, so repeating sequence means if you want to design triangular one, so you can say like that it is repeating response. Okay, so triangular, sinusoidal, or a repeating response. Okay, so if you want to generate only for the single pulse, so it is not repeating. Okay, so as per your requirement you can go for that specifications. So what you want, repeating signal or non-repeating signal. Okay, these signals are utilized in testing Okay, testing, designing, troubleshooting. Okay, so and the repairing electronic devices like that way. Okay, apart from that artistic uses as well, the signal generators also modulated sinusoidal output signal with other signals. Okay, this feature is the main distinguisher between the signal generators and the oscillator. Okay, I think all of you are able to understand the purpose of the signal generator and the oscillator. When an unmoduled sinusoidal output is generated by the signal generators, then they are said to be produce continuous height wave. Okay, signal. Then when they produce the modulated output signals, okay, can be square wave extremely applied with the sine wave, pulses, triangular wave, or the impulses also be sometimes, or sometimes more complex signal as well as internally generated sine wave. Okay, so throughout the amplitude modulations and the frequency modulation, so you can vary the amplitude of the signal as well as you are able to variation the frequency. Okay, can be used. Yet amplitude modulation is generally employed. The figure here you can see the figure of the block diagram. The principle of the amplitude generation and frequency modulation can be shown respectively. Means here you can see the diagram A, figure A is for amplitude modulation. Means you can see that amplitude is different. Okay, figure B is responsible for frequency modulation. Frequency modulation means frequency is different. Okay, means you can see like that different width, frequency width you can observe. Okay, like that you can say like that block diagrams or signal generator. So this is the block diagram of the signal generation. Two things are there: frequency adjustment, one portion is there for the frequency adjustment, another is there range selector. Okay, so RF oscillator means radio frequency oscillator, carrier frequency. So if you change that pulse frequency, so definitely all the things, buffer is also the important thing. Frequency driver is there, so buffer amplifier, output amplifier, attenuator, so output modulated signal. Okay, so frequency change and wave shape selectors. Okay, frequency changer and the wave shape selector, so modulations, oscillations are there, so output amplifier. So all the things are the, it's block diagram. It's a generic block diagram, you can say like that. Okay, so as per the application it will change. So normally the purpose of this one, purpose of this measuring device is it can provide you that two type of signal. One may be amplitude modulated signal, another one is your frequency modulated signal. Okay, for providing the appropriate signal for the calibration and testing, the signal generators are mainly employed. Okay, they are also used for troubleshooting over the amplifier circuit used to electronic and the communication circuit. Mainly you know about that FM radio. Okay, so you know that. So where what in FM radio you are changing the frequency range, means you are changing the frequency of the carrier signal. So what is the purpose of carrier signal? In FM radio you are providing that you are developing some of the carrier signal. That carrier signal is emitting from your radio. Okay, then in your environment, so all the radio channel, different FM channels having some of their frequency range. Okay, so that is available in your environment. So that carrier channel, so you are set one channel. Okay, and that means what happen, you are sending that carrier frequency of that channel. Okay, then what happen, if you sending that carrier channel, that can carry the fixed FM channel from your environment to your radio and you are able to hear it. Okay, so that's the important issue. So the carrier that's the motivation for the carrier frequency. Okay, so that is provided by this signal generator. Okay, the radio frequency, that is called the radio frequency RF oscillation applied for the producing a carrier waveform. Okay, that is called that carrier waveform whose frequency can be attenuated or the tuned. Okay, can be tuned typically from 100 kilohertz to 40 megahertz. Okay, with the help of the vernier dial setting, range selector, switch carrier wave frequency can be varied the display. Okay, the frequency driver are employed to determine the range. Okay, and an oscillator of the frequency stability is kept very high at all the frequency range. Okay, so that's the purpose of that devices. Okay, so what are the most important or working that is given over here? So LC filters process are given the following measuring can be taken attended with a suitable frequency output. Okay, so regulated power supply is required to reduce the change of supply frequency, the change of frequency, the output voltage. Okay, it is required. In separate oscillator of the circuit, buffer amplifier is used. Okay, then temperature compensating device also is suitable for temperature causes the oscillator frequency. So temperature should not be changed because the changing of the temperature may cause that changing of the frequency. So frequency should not be changed. So you have to compensate the changing of the temperature. Okay. In LC oscillator is required a quartz crystal oscillator. Okay, that will provide you the clock pulse. Okay, the accurate clock pulse. So due to the oscillation is employed to achieve the high Q factor and the instance of the 20,000. Okay, when the audio frequency is modulating signal and generating the another very stable oscillator is called the modulation oscillator. Okay, for changing the amplitude and the frequency or the produce the signal that will be used over there. Then provision is also employed to get the several types of waveform much as the pulse, square, triangular oscillator. Okay, modulating frequency and the radio frequency signal are applied to broadband amplifier. Okay, called as a output amplifier. Okay, the modulating of a percentage of the indicated the adjustment of the meter. A control device can be adjusted model up to 95%. The amplifier output is then sent to an attenuator and at last the signal reaches the output voltage of the signal generator. And output meter also be there, final stage of output signal. So different processes are there, then ranging of that RF oscillator is given the signal performance depending on the accuracy. Okay, so 0.5 to 1% dial settings means tuning range, how much you are going to be tuned. Okay, so all are there. Okay, so you have to understand those things. So depending upon the purpose of the application, the various type of signal generators available. Okay, no device is suitable for the all possible applications. So you have to use distinct devices for individual applications. So what are that application? Multimedia computers, audio software, tune generators, signal generators have become the more user friendly and the versatile application of these devices. I think all of you are able to understand different applications of the devices, digital electronic devices, and some question may come. Okay, so like that short note type question may come in this portion. So okay, so if you have any doubt you can ask me. So today I have covered about most important, some of the most important digital electronics measuring devices. Okay, like your digital multimeter, digital voltmeter, frequency meter. Okay, and finally signal generators. Okay, so so if you want any any discussion you can ask me. Okay, otherwise I can close this session. Okay, so I think there is no question from your side. Okay, so thank you for today's session. Okay.